let's take a few minutes to get acquainted with the basics of line integrals. We're pretty familiar with the idea of going from a to b and integrating some function with respect to x or with respect to some other variable. And this is simply an interval on a number line from a to b. Okay? But in this case, a line integral follows a path, c, from an initial point to a terminal point, and we're integrating not with respect to x or y, but with respect to arc length, ds. So this is an entirely different animal. But once again, what comes to our rescue is the fact that we can substitute for these things. In particular, let's take an example where I'm in the XYZ system and I have a circular arc, a semicircle, okay? And in this semicircle, on this semicircle, I'm going to build something, okay? I'm going to build myself a kind of fence, all right? And in other words, this is going to be my x-axis. This is my y-axis. I picked it this way for the convenience in the sketch. And I have decided to build a fence where the height is 4 minus 2x, and this circle is of radius 2. Okay? So at the beginning, when I plug in x is 2, I get 0. And when I get to the far side, where x is negative 2, it's going to be 8. So there's going to be an 8-foot fence at one end. I have no idea what this is for, but this is what we're going to do. And the integration is going to be with respect to s, because that's our linear measure. And c is going to be that semicircle. Now, how do you do this? Well, the easy part, at least I hope it's fairly easy, is that you know that x equals 2 cosine t and y equals 2 sine t will give us a nice parameterization of that semicircle, provided, of course, that t goes from 0 to pi. All right? And here's a fun fact. We know that ds is dx dt squared dy dt squared, added together, square root dt. And that is the key tool that we're going to need for this. So my integral is going to require me to substitute for x. I'm going to have to substitute for ds, and my limits of integration will be 0 to pi. So let's go to work. We know what dx dt is. It's just minus 2 sine t. dy dt is 2 cosine t. All right? So when we put this together, ds is going to be the square root of 4 sine squared t, 4 cosine squared t, and dt. Well, this just adds up to 4. So we end up with 2 dt. Let me copy down my integral. So my integral, c, 4 minus 2x ds, is going to be the integral from 0 to 2. 4 minus 2 times, now remember, x is 2 cosine t, and ds is going to be 2 dt. In other words, 0 to 2, this is 4, and there's a 2, so it's 8 times 1 minus cosine t dt. In other words, 8 times the quantity pi minus sine t from 0 to pi. Now, how do I do that? This is pi. This is supposed to be pi. Okay, give yourselves extra points if you caught that. 8 times pi minus sine pi is 0, and 0 also gives us zeros, 8 pi. So, whatever this fence is for, I know that the square footage, or square meters, or whatever units we're using, the square area is 8 pi. That's one example of an application of line integrals. It's not, however, the most interesting. One of the most interesting applications uses vector fields, which is kind of what you would expect since we just saw vector fields and now we go directly into line integrals. So check this out. Suppose you have the integral, line integral over a path of f dot t ds. F is our vector field. T is our unit tangent in the direction of travel along C. And ds, of course, is the differential of arc length. I hope you remember this, but once upon a time, we learned that if you take the derivative of your position vector with respect to arc length, that's when you get t. In other words, dr is t ds. So, if you don't mind playing with notation, this right here becomes dr. This is fairly common usage. And remember, f, if it's a three-dimensional function, is often just called p, q, and r for its three-component functions. And r, of course, which I refused to call x earlier, you may recall, is xyz. It's just your position vector, which comes from the parameterization of your curve. And dr will just be dx, dy, dz. So what happens? You come over here and you substitute. The name of the game in evaluating line integrals is substitution. Here is p, q, r. Dot product, okay, dx, dy, dz. Write it out. And now we have the traditional notation for line integrals. This notation goes way back. And you need to be able to recognize that. If I go back to this original statement, I mean, here we have line integral with respect to arc length, and for some reason we're integrating f dot t. Well, if this is a force field, and you're dotting it with the unit tangent in the direction of travel, you are finding the component that's doing work. So this is very often simply the definition of work. This is what you would compute if you want to find out the work done by this force over this trajectory c. Let's do an example and see how well we can make this work. Let's have a parabolic path from 0, 0. Call this c, and this is going to be 4, 2. All right? And I will parameterize this. And so to parameterize this, r of t is going to be what? Well, for my x component, I'm simply going to have t squared. And for my y component, I'm going to have t, as t goes from 0 to 2. In other words, x equals t squared, this is x, and y equals t. Check it out and see if you agree with that. See if it makes sense to you and that you could do it yourself if you had a similar problem. And I'm arbitrarily going to pick a function to do. So over C, I'm going to do a two-dimensional line integral x plus y dx plus x minus y dy. And we know dx is 2t dt and dy is just dt, so substitute away. Integral 0 to 2 t squared plus t times 2t dt plus t squared minus t dt. Okay, from here you're going to get the first part. You're going to get 2t cubed plus 2t squared, and here you get another t squared, you get a minus t, and you get dt. Collect like terms. 2t cubed plus 3t squared minus t. And I differentiate this with our friend the power rule. So let's see, t to the fourth over 4, 1 half t to the fourth plus t cubed minus 1 half t squared from 0 to 2. Okay, let's plug into this. 2 to the fourth is 16, take half, 8. 2 cubed, 8. 2 squared is 4, half of that is 2, subtract. The answer is 14. We have now done a couple of examples of line integrals, both the plain old ds version and a slightly more sophisticated version along a parabolic path for you.